Dear colleagues, we present to your attention a report on the topic, influence of the size of hematite and magnetite ores on the parameters of the sintering process and the quality of the sinter. Along with magnetite ores, hematite ores are of significant value for ferrous metallurgy. Analysis of a mineral resource base of mining and metallurgical enterprises 1 to 3 indicates the prospects of their use to expand industrial reserves of iron containing raw materials. However, the technology of their agglomeration has characteristic features that distinguish them from traditional magnetite raw materials. Despite the vast amount of information on the patterns of formation of the structure, mineralogical and phase composition of iron ore agglomerates, there is no single point of view either on the mechanism of formation or on the influence of individual factors on qualitative characteristics of iron ore sinters. This circumstance makes it necessary to study the conditions for obtaining iron ore sinter from hematite ore, depending on its size. The purpose of this study is to establish and compare the regularities of changes in the indicators of the sintering process and the quality of sinter from the size of hematite and magnetite ores in sinter charges based on them. To determine the effect of the type of ore, the study did not use a mixture of different ores, but two separate ores, ore A, containing 100 Wt% magnetite, and ore B, containing 94 Wt% hematite. Figure 1 shows the size of the mixtures of fractions of the individual ores. To characterize the mixtures, the Hs50 index was used. This is the mesh size of the strainer through which 50 Wt% of the mixture passes. When evaluating the research results, it turned out that the return size fluctuated greatly. For each ore, based on ALSIF recovery analyses, a mix of analysis was calculated, which is graphically presented in Figure 1b. It was found that the return during sintering of hematite ore B has fewer fine fractions than the return during sintering of magnetite ore A. The oxidation state of the return in individual experiments also fluctuated. It was determined by calculation. When using ore A, it was 94%, when using ore B 97.3%. Thus, the dependence of the oxidation state of the return on the oxidation state of the charge is visible. Since the return flow rate of 40 kg, 100 kg of ore mixture was kept constant. The return had a significant effect on the properties of the entire mixture. In this regard, in Figure 1c, D shows the size of the entire charge A and the entire charge B in contrast to pure ores. Significant changes are visible. All sieving curves are biased towards larger fractions. Figure 2, A, B and D show the gas permeability of the sinter charge in the bowl as a function of the size of the ore and the entire charge. The best gas permeability of hematite ore is observed when the particle size is Hs50 equals 0.7 to 0.8 mm, or for the size of the entire charge Hs50 equals 0.9 to 1.0 mm. It was also found that for hematite ore these values in the area of fine fractions fluctuate strongly. The same picture is observed for the second moment of time, Figure 2, B, D. The higher gas permeability when using hematite ore can be explained by the greater strength of the lumps due to the adhesive components. With strong waterlogging of the sinter charge in the lower part of the bowl, less strong destruction of the formed lumps occurs here than during sintering of the charge from magnetite ore. Figure 3 shows the dependence of the sintering performance on the size of the ore and sinter charge. In the same way as for gas permeability, differences between the two ores were found for the sintering performance in the area of fine fractions Fig 3 and B. These differences are found when the value of the Hs50 index for ores starting from 0.6 mm and for the entire charge starting from 1.0 mm, which coincides with the corresponding data for gas permeability. Figure 3, B and D, it is clearly seen that with an increase in the fraction of -0.1 mm, productivity decreases. The difference is again noticeable for ores A and B in the area of fine fractions, and for ore starting with a fraction of minus 0.1 mm 5 Wt%, and for the entire charge starting with a fraction of minus 0.1 mm 7 Wt%. These differences can also be explained by the different lumpiness of the ore. Figure 4 shows the dependence of the demand for dry coke on the size of the ore and sinter charge. At the same time, there is a noticeable difference in the demand for coke for magnetite and hematite ores. On the other hand, the influence of the ore size is noticeable. Starting with a certain grain size, the need for coke is constant or increases very slightly. The corresponding value of the Hs50 indicator for the whole charge is 1.4 mm. With a smaller grain size, the need for coke in both cases decreases to a sharp minimum, especially for sinter charge. Figure 5 shows the dependence of the content of the fraction plus 25 mm in the agglomerate on the index Hs50. With an increase in the size of hematite or B, a continuous decrease in the yield of the agglomerate fraction of plus 25 mm is observed, while for magnetite or A, starting with an Hs50 of 0.8 mm for a sinter batch of 1.0 mm. This value remains constant. In general, the yield of the plus 25 mm fraction in the agglomerate from magnetite ore is higher than from hematite, which indicates their different sintering capacity. Tests have shown that the abrasion of the agglomerate from hematite ore is 7.6 to 5.3 Wt%, and there is a tendency to decrease it with an increase in the size of the ore. For agglomerate from magnetite ore, abrasion is 8.0 to 6.4 Wt%, and in this case there is also a tendency to decrease it with an increase in the size of the ore. The maximum abrasion was observed at an Hs50 value for a charge of 0.6 to 0.7. Figure 7 shows the dependence of agglomerate abrasion on the size of the ore and sinter charge. At the same time, a decrease in abrasion is seen with an increase in the size of the ore batch. No differences were found between magnetite and hematite ores. The points for both ore grades are evenly spaced around the straight line. When determining the dependence of abrasion on the content of the fraction minus 0.1 mm, it was found that when the content of this fraction is more than 10 Wt%, the abrasion remains constant even at very unfavorable values 32 Wt%, and decreases only when the content of the fraction minus 0.1 mm is below 10 Wt%. As already mentioned, under these conditions, the demand for coke with an increase in size increases. However, at the same time, the FeO content in the finished agglomerate also increases. Fig. 8. It can be seen that with an increase in the FeO content, abrasion decreases. It can be assumed that this influences the improvement of abrasion with increasing particle size. Figure 9 clearly shows the difference in the demand for coke when using hematite and magnetite ores. To achieve the same productivity, this requirement for both ores differs by 1.5 to 2 kg of coke, 100 kg of ore mixture. The demand for coke also determines the FeO content or the oxidation state of the agglomerate. With the same fuel consumption, the oxidation state of sinter from hematite ore B is 2 to 3% higher than sinter from magnetite ore A. The agglomerate was tested for reducibility at a reduction temperature of 1000 degrees Celsius with simultaneous loading of the sample. The amount of oxygen withdrawn was measured in Wt% per minute at a reduction rate of 40%. The obtained indicators of recoverability can be considered very high for both ores. With an increase in the grain size, a certain decrease in reducibility is noticeable. But since with an increase in particle size, the need for coke increases, and thereby the FeO content in the finished agglomerate. Fig. 10 shows the dependence of the recoverability on the FeO content. With an increase in the FeO content in the agglomerate, the reducibility decreases. It is also seen that the reducibility of agglomerates from magnetite and hematite ore mixtures is the same. Experiments on sintering artificially obtained mixtures of fractions from magnetite ore A and hematite ore B made it possible to reveal a number of features of this process depending on the grade and size of the ore. In particular, it can be concluded that the gas permeability of the layer and the sintering productivity increase with increasing size for both ores. Only in the area of very fine fractions was there a difference between hematite and magnetite ore. Better gas permeability and higher productivity of sintering in the area of fine fractions for hematite ore can be explained by better lumpiness of the charge due to the higher content of adhesive components. The minimum need for fuel was observed at an average particle size. The best values of the drum strength of the agglomerate were obtained with different sizes of hematite and magnetite ores. And the nature of the change in drum strength from the size differs significantly for these ores. A certain increase in strength charge and increase in the size of both ores or sinter mix was observed with an increase in the FeO content in the agglomerate. The oxidation state of the sinter at the same size and a certain predetermined consumption of coke is the same for both the hematite ore sinter and the magnetite ore sinter. The report is over. Thanks for attention.